Here's the entire recipe for a black hole. In full, take a large amount of mass and make it smaller. That's the whole method. 2 ingredients, mass and smallness, and you're done. So why hasn't anyone done it? Why does nature apparently need an entire dying star and sometimes a supernova on top of that just to pull off what sounds like a party trick? Today we're building one ourselves, hypothetically, and we're going to run face first into every wall physics has ever built. Start with something you already understand. Throw a ball straight up. Gravity pulls it back down. Throw it harder and it climbs higher before gravity wins. There's a speed for Earth about 11 kilometers a second, where you throw it hard enough that gravity never wins. It just leaves. That speed has a name, escape velocity. And here's the detail that matters more than the name. Escape velocity isn't fixed to a planet. It depends on exactly 2 things: how much mass you're escaping from and how tightly that mass is packed. Same mass, packed tighter, and the number climbs. So ask the obvious follow-up. What happens if you keep packing tighter? Eventually, escape velocity stops being 11 kilometers a second and starts approaching faster than light. And light is the fastest thing there is. Cross that line and nothing gets back out. Not light, not radio waves, not a strongly worded letter. That line has a name, the event horizon. And the radius where it forms has a name too. The Schwarzschild radius, worked out in 1916 by Karl Schwarzschild, who solved Einstein's equations for this exact scenario from an army trench during World War I, which feels like it should be either more famous or more of a warning. Now, you're probably picturing the plan as gather a lot of mass, pile up planets, stack stars, but that's not actually the lever you're pulling. Watch this number. Compress the entire Earth, all 6 sextillion tons of it, down to under 2 centimeters across, and it becomes a black hole. Not more mass, the exact same mass, just smaller. The recipe was never more, it was always tighter. So why not just build an enormous hydraulic press? Because nothing you could build is strong enough. Every solid object you've ever touched is held up by electromagnetic repulsion between atoms, the same force stopping your hand from passing through a table right now. Beating that at planetary scale needs a force electromagnetism can't out-argue. Exactly one qualifies, and you already know its name. Gravity, which means the only real tool for building a black hole is a black hole's own future gravity, enough mass that its own weight does the crushing, no outside contractor required. Conveniently, this is also the only method the universe has ever actually used. A star spends its whole life in a standoff. Gravity, pulling in, fusion, pushing out, a multi-billion year tug of war that fusion is guaranteed to lose. Eventually, once the fuel runs out, what's left behind depends entirely on how much mass was pulling. A star like our sun collapses into a white dwarf and stops there, held up by electron degeneracy pressure, a quantum rule that refuses to let electrons crowd any tighter, like a mosh pit that's physically hit its limit. Add more starting mass, and even that quantum stubbornness gets overrun. You get a neutron star instead, held up by the same trick, one rung down using neutrons. Add still more, and you cross a line. Nobody has measured precisely yet, somewhere around 2 to 3 times the sun's mass, packed into a collapsing core, where even neutrons give up the fight. Nothing is left to push back. Gravity wins the argument outright, and whatever wins becomes a black hole, which, incidentally, is a genuinely bleak sentence to read about your own future if you happen to be a star several times heavier than our sun. Sorry, but you're not a star, hypothetically. So if gravity is the only tool anyone actually trusts for this job, and you don't have a spare one lying around, what's left? Physicists have floated stranger routes. 1. Collide particles, hard enough in a small enough space that if certain theories about hidden extra dimensions turn out to be correct, you could briefly concentrate enough energy to open a microscopic event horizon. This is a real hypothesis, and it's the one that made headlines in 2008 when the Large Hadron Collider switched on, prompting a handful of people to worry it might swallow the planet. It didn't, and it wouldn't have. The physics on this is settled. Even in the most exotic version of the idea, any black hole small enough for a collider to produce would evaporate in a fraction of a second, converting itself back into ordinary radiation before it could do anything as dramatic as eating Switzerland. There's a second, stranger route, and it doesn't require matter at all. Mass and energy are 2 forms of the same currency. That's the entire idea behind Einstein's most famous equation, and gravity only cares about the total. Concentrate enough energy from light alone into a small enough space, and space-time curves exactly as hard as if you'd use matter instead. Physicists even have a name for the hypothetical result, a Kugelblitz, a black hole made entirely of trapped light. Nobody has built one or ever will. The energy required is more than every power plant on Earth has generated across all of human history, several times over. But the fact that it's allowed at all is exactly the kind of detail relativity drops on you without warning. So say you pull it off by whichever impossible method. What's actually inside? General relativity's answer is blunt. At the center, density goes infinite, and the equations simply stop working. Most physicists don't read that as there's a literal infinitely dense point in there, so much as general relativity has hit the edge of what it knows how to describe. The honest answer is that nobody knows what's really at the center of a black hole, because answering that requires merging relativity with quantum mechanics into a theory of quantum gravity, and nobody has finished building one. That's not a gap anyone's hiding. It might be the single biggest open question in physics, and if that didn't fully land, that's fine. It's not supposed to yet. The people who study this for a living are working from an incomplete map too. There's one more twist. In 1974, Stephen Hawking argued that black holes aren't perfectly black after all. Quantum effects, right at the edge of the event horizon, should let them leak radiation incredibly slowly, losing mass as they go. Nobody has ever directly observed it happening, but the reasoning behind it is trusted enough that it's treated as close to settled. For a black hole built from a whole star, that evaporation would take unimaginably longer than the current age of the universe, so don't wait up. But the math flips entirely for a hypothetical microscopic one. The smaller it is, the faster it evaporates, which means if you ever did succeed using a collider or a wall of lasers, your black hole's next move wouldn't be to eat anything. It would be to vanish almost immediately in one small flash of its own light. So the recipe really is that short: mass and smallness. 2 ingredients. It's just that the only kitchen in the universe equipped to cook it is gravity itself, working at the scale of a dying star with no substitutes accepted. Everything else, the colliders, the lasers, the marble that used to be Earth, is us hypothetically borrowing a trick. One force has been quietly running since the first stars burned out. If that's your idea of a good time, subscribe.